Hi, my name is Michael, and I'm excited to share our work with you on automating enterprise workflows with multimodal foundation models. As a brief outline before we start, I'll begin this talk with the motivation and prior work, walk through our vision for an end-to-end system to automate workflows, then discuss some preliminary results on a benchmark before showing you a demo of applying our system on a real-world healthcare workflow and concluding with some next steps. But first, what is an enterprise workflow and why should you care? When I refer to an enterprise workflow, I broadly refer to any task done on a computer by an employee of a large organization. For example, a sales rep filling out a customer support ticket or a doctor submitting an electronic medication order. These digital workflows form the core of our modern economy, with 92% of jobs requiring the digital skills that you can see in this video. Unfortunately, this comes at a cost. The average knowledge worker spends roughly 3 hours per day on tedious digital tasks that are tangential to their core responsibilities. And the cumulative economic impact is staggering. McKinsey estimates that roughly $4 trillion in productivity gains are waiting to be unlocked by automating these processes. Obviously, I'm not the first person to realize this, which brings me to the significant amount of prior work that's been done on automation. In particular, the standard technology for enterprise workflow automation today is called robotic process automation, or RPA. RPA is essentially a low-code tool for creating bots which follow hard-coded rules to accomplish a narrowly defined task. Popular vendors include UiPath, which is shown on the screen here, Blue Prism, and Automation Anywhere. Narrowly scoped RPA deployments can have very high ROIs and roughly double the speed of workflows. However, widespread adoption of RPA has been limited by three key failure modes which surfaced in our interviews with technology leaders at a hospital and B2B enterprise. First, RPA is costly to set up as it requires trained specialists to encode the workflow in the low-code editor you saw in the previous slide. In our case study of a B2B enterprise that tried using RPA for invoice management, it took roughly 12 months to go from project kickoff to deployment. Second, RPA bots are brittle. This is due to their reliance on hard-coded rules. In our B2B case study, the RPA bot was initially only 60% accurate and took 6 months of refinement to reach 95% accuracy. Third, RPA requires continued maintenance and oversight from humans. Again, in our B2B case study, the bot that was developed by the company ended up requiring continuous monitoring by 2 employees. And more details on this case study, as well as a case study that we did of a hospital, are available in our paper. These issues have motivated a ton of recent work in applying multimodal foundation models like GPT-4 and Claude, which have demonstrated robust reasoning, world knowledge, and planning abilities to these workflows. However, there remains a significant gap between this research and enterprise-ready solutions, which motivated our work in designing an overall system that could leverage the capabilities of these foundation models to supplant the entire traditional end-to-end RPA stack. So what exactly then is our vision? Well, that brings me to the next section, which describes our approach, which is proposing a system called Eclair, short for Enterprise Scale AI for Workflows. Eclair aims to solve the 3 primary limitations of traditional RPA by applying multimodal foundation models across all aspects of the workflow automation tech stack. First, in the demonstrate phase, we passively record human demonstrations of a workflow, then have Eclair distill these recordings into actionable documentation. This lowers setup costs by avoiding the need to hard-code RPA bots and helps to incorporate tacit domain expertise. Second, in the execute phase, Eclair interacts with the computer in the same way that a human would, via visual observation of the screen and navigating via clicks, keystrokes, and scrolls. This improves reliability of workflow execution by avoiding reliance on brittle APIs and hard-coded if-then statements like in traditional RPA. Finally, in the validate phase, Eclair is able to self-verify that the actions it took were correct. This can combine programmatic heuristics with foundation model based assessments, which reduces the need for human oversight. So, given these 3 components of our proposed system, how far are we actually from realizing this vision of going end to end, from having a person demonstrate a workflow, doing a screen recording, and then basically getting end-to-end workflow automation out of Eclair. In this next section, I'll walk through some preliminary results that we've obtained when evaluating each of these three components on a subset of 30 web navigation tasks that we sourced from a popular benchmark called Web Arena. And these 30 tasks were specifically chosen because they had been previously unsolved by baseline methods. And on the right here, you can see an example of what one of these digital workflows sourced from Web Arena looks like. First, we considered the demonstrate phase. The goal here was to test if a multimodal foundation model could transform a video recording of a workflow into a standard operating procedure, which is basically just written documentation of every action that is taken in a workflow. For this experiment, we had a human annotator complete one of the 30 workflows I previously mentioned. We then fed this recording through GPT-4 and had it output an SOP containing a list of every step taken in that video demonstration. We tested several different combinations of context to be included in the prompt. WD in the table, the top row of the table that you see here, stands for just providing the workflow description to the model. WD plus KF also includes screenshots of key frames from the video recording itself. And WD plus KF plus ACT also includes a textual log of all actions taken, so clicks, keystrokes, and scrolls. And what we find here, as you can see in the bolded red box, is that when given enough context, GPT-4 is capable of outputting highly accurate SOPs, making an average of roughly only one mistake every 9-ish steps. Next, we tested the execute phase of Eclair. To execute the workflow, we envision Eclair working as follows. First, Eclair takes a screenshot of the current state of the laptop. Next, Eclair segments relevant page components using a locally hosted vision model. Third, Eclair uses a larger multimodal foundation model, in our case we use GPT-4, to plan its next action to take based on the current screen state, its action history, and an SOP describing the steps of the desired workflow in natural language. After getting the action prediction, we then use Python to actually execute it on the computer, and we repeat this process until Eclair determines that it has successfully completed the workflow. In our experiments, we find that including an SOP in the prompt more than doubles Eclair's ability to complete these difficult workflows. In the table shown here, the top row is Eclair without using an SOP, and the bottom is Eclair with the benefit of having an SOP to rely on. The left-hand column shows the accuracy of its individual action predictions. So, given a specific action, is this specific action correct? And the right-hand column is the overall success rate of completing the entire workflow. So given a full workflow with many steps, can Eclair successfully complete every step of that workflow? And the jump in performance that you see in the highlighted box illustrates the importance of capturing workflow-specific domain knowledge via SOPs. And the great thing about this is that the SOP is human interpretable, right? It's just natural language, and thus it provides a natural interface for guiding model behavior. Finally, we tested the validate phase of our proposed Eclair system. There are several levels of validation that we might care about, but we've highlighted two primary ones here. First, on the left, actuation. As the model runs through a workflow, are the actions that it has planned and wants to take actually being successfully executed? So if I say, hey, I want to click this box, and the screen changes, did I actually successfully click that box? And then secondly, on the right-hand side, workflow completion. After the model finishes, was the workflow that it was supposed to be executing actually successfully completed? And in our benchmark results, we find that foundation models are able to do both to some extent. So framing each of these two questions as a binary classification task, we find that Eclair is able to achieve F1 scores of around 0.9 on both tasks. However, an important thing to note is that in the context of complex enterprise workflows with dozens of consecutive steps, this is not sufficient, as a single misprediction about an action can derail an entire workflow. And thus we believe that self-validation remains a key area for future research. So we've outlined our vision for how to use multimodal foundation models to supplant RPA, and showed promising results on a small benchmark indicating that this vision is achievable. But talk is cheap. how does this actually translate to a real world use case? So that brings me to our next section, in which I will share with you a proof of concept demo of Eclair applied to a real world hospital workflow in collaboration with Stanford Healthcare's Nursing Informatics and Innovation Department. Namely, placing a telesitter order in Epic, which a nurse might do if a patient needs continued observation, but there's not enough staff to do it in person, so they need remote monitoring of a patient. And so, how do we apply Eclair to the challenge of automating this telesitter order? Well, first, we record a nurse completing the telesitter order workflow, and you can see the actual raw recording that we got from the nurse on the left-hand side here. This entire workflow takes about 1.5 minutes, and from this recording, we automatically generate the stuff that you see on the right-hand side. So obviously we capture the full screen recording, but we also track all of the clicks, keystrokes, and scrolls that were taken by the nurse, as well as screenshots synced to every action of the keyframes of the workflow demonstration. And as you can see here, it's a pretty complex workflow. There's a lot of buttons being clicked, forms being filled out, pop-ups, and this all exists within a complex interface, namely Epic, which is one of the most popular electronic health record softwares. After we get this recording, the next step is we take the screenshots and action trace that we generated and we feed it through GPT-4 to generate an SOP, the standard operating procedure that I mentioned previously, which captures every step of the workflow. Third, we load up a sandbox instance of Epic, the electronic health record software, and we give Eclair full control over my laptop. So it can click, type, scroll just like a human would. Fourth, we give Eclair the SOP that it previously generated, as well as the instruction for the workflow. So the instruction is, place a telesitter order for this patient, and then we have Eclair autonomously complete the workflow. And you can see on the right-hand side here, here is a sped-up video recording of Eclair actually completing this workflow, navigating through Epic, and doing exactly the same steps that the nurse had previously demonstrated for this patient. And if you want to see the full video demo, please feel free to scan the QR code in the top left to see the full video recording. Finally, we take the recording of Eclair executing the workflow, we feed it back through GPT-4, and basically ask it, was the workflow successfully completed or not? And we're able to get it to correctly validate that the workflow was completed. So we hope that our work so far has showed the exciting potential for foundation models to revolutionize all parts of the workflow automation stack, both with our preliminary benchmark results and our real-world nursing demo. However, there's still significant room for improvement and future work. Key open questions include error handling and self-monitoring, how to effectively transfer control between human operators and autonomous agents, for example, if you need a physician sign-off for a specific action, as well as other important contributions such as building larger data sets of these sorts of workflows for training and evaluation. Finally, I'd like to conclude by thanking all my collaborators and advisors for their hard work and mentorship. And if you're interested in learning more about our work, please feel free to reach out to us at either of the email addresses listed at the top of the slide here, or visit any of the links on this page to learn more about our work. Thank you so much for your time, and appreciate the consideration.